interaction observed in R and K states.
Thank you, Chairman. So today I'd like to talk about this topic, but I'll talk about the metal support interaction. That is important interaction in the supported catalyst. So metal and oxide there are many examples on the metal supported on oxide. For example, the metal oxide semiconductor, and of course catalyst. Catalyst, this is the gold on catalyst. It's very important and famous catalyst of the Professor Harda. And why we use oxide? Because metal is precise, means a high cost. Therefore, we want to have very small metal cluster in order to increase the surface area. So the oxide surface have a large surface area. Therefore, the metal cluster can easily be dispersed on oxide surface. But the problem is the function of oxide is only to disperse the metal cluster. This is one example. The CO hydrogenation of ruthenium that is prepared from the previous silicon carbon clusters. They put it on various oxide supports. We put the same material on the various oxide supports and see this CO hydrogenation reaction and changing the product distribution and activity. So that is the origin of my question. Why such a difference occurs? It means there should be some electronic interaction between them. So the question is, what type of interaction between them? There should be on the oxide surface, there should be metal, cation, and anion, oxygen. So there are two possibilities. One is metal anion interaction, the other is metal cation interaction. And what is the bonding feature? For example, metal anion interaction, is it covalent bond or on the water style? So how to see this interface structure? Usually structure analysis is done by the diffraction method. However, diffraction method is difficult because powder, we use the highly dispersed, so there is no long range order. The other way is to use microscopy. So this is one example, the gold on the titanium. So Professor Tanaka's one of the lectures shows it is possible to identify each atoms nowadays. However, it's still difficult to get the bond distance. So another way is to use spectroscopy. Today we talk about this EXAFS technique, X-ray absorption fine structure technique. This is the technique to give us the metal oxygen or metal, another surrounding atoms, bond distance and Cauchy number. Oh, sorry. Oh, I missed one picture. So, I should say something about EXAFS. EXAFS is the X-ray absorption fine structure. That is a spectroscopy. And when the X-ray is absorbed by atoms, the core electron is excited as a photoelectron, and photoelectron interferes with the surrounding atoms. And as a result, there should be some modulation. I should show some spectrum here, but I missed this one picture, sorry. And another feature of this EXAFS is polarization dependence. Amplitude of EXAFS have the polarization dependence So this theta here is the angle between electric vector and bond direction. That means if we use single crystal flat oxide surface and put metal cluster on it and put X-ray electric vector parallel to the surface, we will have bond information just this direction, so parallel direction. On the other hand, if we put the X-ray polarization vector to the support direction, we'll have bonding information about metal support. But the problem is we have to use single crystal. Normally we use powder sample, therefore we have a lot of metal clusters on it. However, if we use single crystal has small surface area. It means cluster concentration, surface cluster concentration is very low. Therefore, we have to use some surface sensitive technique. We develop total reflection fluorescence mode to detect cluster, very low concentrated cluster on the single crystal surface. So, this is the technique we have developed. Polarization dependent total reflection fluorescence EXAFS. That enabled us to detect 1 times 10 to 13 square per square centimeter concentration metal species. So this is one example. If we put X-ray direction, something like this polarization direction to the support direction, in this case, we can get EXAFS oscillation to this direction. So this EXAFS oscillation includes metal support interaction. On the other hand, if we put X-ray electric vector parallel to the surface, in this case, we have information along this direction. No information about metal support interaction, but information about metal-metal interaction. This is a picture, the system we have developed. And as I told you, we use single crystal. We use titanium oxide, 110 single crystal, because titanium oxide is a good battery support, and sometimes it is used for the camera. And TiO2 1-hour surface is the most well-known single crystal. So this is STM picture. There is some white line running in this direction. This direction is 001 direction. So this is a model structure. Blue one is titanium. Here, 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 here. And oxygen row, large ball are oxygen. So oxygen row running along 001 direction. And in between oxygen row, there are titanium exposed to the surface. And this STM picture, white line corresponding this titanium row. When we put early transition metals, for example here, molybdenum, what we found is molybdenum atoms are strongly interacting with oxygen, surface oxygen. When we put molybdenum and using the alkaline solution containing some impurity, alkaline metal impurity. In this case, we have such a type of the EXAFS oscillation. It indicated that the molybdenum, tetrahedral molybdenum, is stabilized on the surface. On the other hand, we put this molybdenum species using ultra pure water, no impurity. In this case, molybdenum dimer here, orange one, molybdenum dimer is attached on this oxygen rod. And if we put molybdenum and reduce the sample, in this case, molybdenum chain is found along the oxygen rod. This is 001 direction. So, in this early transition metal, in this case, what we found is metal strongly interacting with oxygen. On the other hand, how about red transition metal? One example is the nickel. We put the nickel on the TiO2, one surface, and measured STM. What we found is we found nickel cluster at a low coverage, 3 times 10 to 13. And this cluster have a unique feature that have the sides. This is size, lateral sides. Lateral sides is almost constant. And the height is almost constant, up to 1 times 10 to 14. And more than that, height starts to increase. It means cluster is stabilized by the interaction with the titanium. What's interaction between them? So we measure EXAFS oscillation, EXAFS. So that this is electric vector along this direction. This is electric vector perpendicular to the direction. And this is perpendicular to the surface. So that we have 3 different EXAFS oscillation, polarization EXAFS oscillation. What we found? We found nickel-nickel interaction in all directions. The second one, we found oxygen interaction in this direction, 1,1,0 direction. And also 1,1,0 direction. But the 1,1,0 direction is stronger. After the analysis, what we found is the cluster structure, something like this. So the blue line is nickel. Nickel is strongly interacting with oxygen. Bond length is 2.2 to 2.5. And this cluster is stabilized probably because this oxygen row and the cluster size is well matched, well fitted well. So in this direction, 6 nickel atoms gives 1.2 nanometer, and 5 breathing oxygen, this oxygen row gives the 1.18 nanometer. So they fit well. So therefore, this matching between nickel cluster and oxygen row gives this stable, stabilized this cluster structure. If we measure, if we put less than this amount, 1 times 10 to 13, in this case, we couldn't observe the nickel cluster by STM. So the very small nickel dispersed on the TiO2 surface. So this is EXAFS oscillation at this very small concentration of nickel. In this case, what we found is nickel is not on this stellar side or the defect side, but on this step side here. So this is a summary of the growth of the nickel on the TiO2 surface. So at very low coverage, nickel does not meet each other. Therefore, it's caught by the it is caught by the step edge. However, if the concentration increases, nickel atoms collide each other and stabilize on the stellar side due to the interaction with oxygen and nickel.